So we're happy to have Ken here to tell us about superconformal multiplets.
Okay, thank you. Yes, I'd like to start off by thanking the organizers for this great workshop and for the opportunity to speak here. The talk will be based on a series of papers with Clay Cordova and Thomas Dimitrescu. And this is kind of just a summary of some of the papers that we wrote going back a couple of years. Our first paper was on 60-1-0 theories, trying to understand if this is 1-0 supersymmetry, trying to understand if there's an analog of the A theorem in 4 dimensions for those theories, and using supersymmetry to relate the conformal anomaly A to some, what I'll call the Tooft anomaly coefficients. So I'll explain in more detail what these different things are, but I just wanted to give kind of a broad overview to begin with. So here, alpha, beta, gamma, and delta are coefficients in an anomaly polynomial, and I'll remind you what the anomaly polynomial is. This is if you turn on some background fields for the R symmetry. So, as I'll review, there's an R symmetry. You can also turn on a background metric, and then there are anomaly polynomial contributions involving the metric. And so these coefficients, alpha, beta, gamma, delta, depend on the theory. And there's some nice papers by Mori and collaborators that give some methods for computing these coefficients in different theories. And once you know those, then you can plug this into this formula, which we argue using supersymmetry, to find the conformal anomaly A of those theories, and then check the A theorem. And this A theorem is going along the tensor branch of 1-0 theories. So 1-0 superconformal theories have a moduli space of vacua with they have 8 supercharges, so it's like 4D n equals 2. So there's a Higgs branch, and what in 4 dimensions would be a Coulomb branch. Here, I use Coulomb and tensor interchangeably, so I'll call this a tensor branch. And then there's just a superconformal theory. So here at the origin, there's a superconformal field theory. And in this first paper, we studied the theory on the tensor branch. Okay. Another paper that we wrote was to classify the supersymmetric deformations of superconformal field theories in 3, 4, 5, and 6 dimensions. And just to give some motivation for this, my own motivation for studying superconformal theories is that, when we first learn about quantum field theory, we study free field theory and perturbations around free field theory. And so by studying those kinds of theories, we can see some subspace of the space of quantum field theories. But we know there's a much bigger space of quantum field theories that include theories that aren't in any way close to free field theories. And so conformal field theories give another jumping off point for studying quantum field theories. So we can start in general with some conformal field theory, and then we can analyze what are the relevant perturbations and see where we flow to in the infrared. We might not be able to follow the flow, but by doing this in different patches, we can study more space in quantum field theories. And if there's supersymmetry, then there's some extra tools for obtaining exact results. So if we restrict ourselves to superconformal field theories, we can study what are the SUSY flows. And there was a nice paper in 4 dimensions, in 4D n equals 1 theories by Green, Kormogotsky, Tachikawa, Seimer, and Wecht that classified the supersymmetric deformations. And so we generalized this to all dimensions, except for 2. We avoid 2 dimensions. And so among the different results, there are no relevant or marginal Lagrangian deformations in 6 dimensions. I'll mention that. And then in the third paper, we kind of studied the general structure of multiplets of superconformal field theories, again in 3, 4, 5, and 6 dimensions. And some of these properties of multiplets we already applied in the first paper and the second paper. So in a way, we should have written this one first. But it turned out to be pretty subtle to study the multiplets. If you really want to classify and study all of the different multiplets, there are various subtleties along the way that I'll mention a bit about. And then we have a work to appear on going back to 60-10 theories in A and some aspects of this formula. So a lot of the talk today will be about kind of this number 3 and then this number 4, and I'll come back to these other things. Okay, so already almost 40 years ago, Nam classified the possible superconformal algebras. So if you look at what a superconformal algebra should be, if we're in d dimensions, we know that we should have a SO d comma 2 subgroup. We want supercharges that are in the spinor representation of this SO d comma 2. And if you look in generic dimensions, you just can't write down a supergroup. The list of supergroups were also studied by mathematicians. You just can't write down a supergroup which contains this subgroup and some fermionic generators in the spinor representation. You can only do it for low d, because for low d, SO8 and lower has some special properties like triality. Here this is SO d comma 2 is SO8. So in 6 dimensions you can use triality. Above 6 dimensions they don't exist. So in 6 dimensions there's a whole family of them labeled by n, and they have 8n supercharges. In 5 dimensions there's only one possibility. This is some supergroup version of F4, which has 8 supercharges. In 4 dimensions, there's again a family of the SU22/n with 4n supercharges. In 3 dimensions, there's again a family of them with 2n supercharges. And in 2 dimensions, you can have different numbers of left moving and right moving supercharges. So these are the algebras. And then, so this multiplets project, you can think of as trying to study what are the representations of those algebras. And this is something that mathematicians could have studied. If you just look at these supergroups, you can ask what are the different representations. And because we're interested in unitary theories, we're especially interested in unitary representations. So we want to have some operators that form a unitary representation. As usual in conformal field theory, we can form this operator-state correspondence, and so we have a notion of the inner product, and we can ask that this inner product preserve a positive or non-negative norm. And if the norm is 0 for some operator, then that operator should be 0. Okay. And just to kind of highlight or preview some things that I'll mention a little bit more about. In this case, so for n equals, well, we could have n equals 1 and 2, and then above 2, we argue that there's no nice stress tensor. So even though there's a whole algebra, even though the algebra exists for arbitrary n, for n bigger than 3 and higher, there's no nice stress tensor.
Is there any way to construct theories which somehow are consistent from some point of view but don't have stress tensors? Or
I don't know. Yeah, you can. For the case of n equals 3, we can write down. Actually, maybe I should say a little bit more. We can write down a multiplet. We can ask if there's a stress tensor multiplet, and there is for n equals 3 a stress tensor multiplet. But the problem with the multiplet is that in order to have the right supersymmetry algebra, we need to have Q. So let me just write here. We should have Q T mu should be 0 up to total derivatives in order to have the right super. You know, this is because we want Q to commute with the P's. So if we construct the charges associated with these T mu nus, the momenta, we should have Q commuting with those. And so we can write down a multiplet for instance, for n equals 3 that has the stress tensor, but this thing isn't satisfied. It's not 0 up. I should say it's 0 up to total derivatives.
So P commutes with it, but not Q. Something like
So recently I heard from Chris Hall that he proposed 3,1 and 4,0 60 series.
I see. So
he has been proposing that for more than 10 years, and somebody was trying to write a field equation for
I see.
4,0 series.
I'm embarrassed to say I don't know I haven't read his paper, so I have to check to see.
The structure is different. They don't have retention of
There's no graviton.
No, graviton, it becomes sort of a strange generalization of emphysemic center field, more complicated representation. So
I see.
5D graviton, here is imagining that you go to, like 5D Yang theory, you go to strong coupling limit and you become 2,0. For 5D supergravity theory, when you go to say infinite or zero coupling of Planck scale, then you go to like 4,0 series.
I see. Yeah, no, I can't say anything useful about that.
So when you say nice before, you meant this condition, right? You said there's no nice.
Yeah, so if you look at the n equals 3 case, for instance, there is a multiplet that contains the stress tensor, and but the stress tensor doesn't satisfy this condition.
So what do you get on the right-hand side of this computation?
So on the right-hand side of here is some other operator in the theory, and there's no, you can't set that operator to 0. Yeah, it's not a 0 norm operator. Yeah, maybe this is a good place to mention a little bit about how these multiplets are constructed. So the idea is that, so usually in the conformal field theory, we start with some primary operator, and then we form descendants with p mu, and so we have k mu. So the primary operator is annihilated by k mu at the origin, and then we can study these p mu descendants. And for some operators, some of these p mu descendants might be 0, and then we say this isn't a short representation of the conformal group. So an example of a short representation of the conformal group would be, for instance, a conserved current. So if you take a conserved current, chain mu, then we know its divergence is 0, so we can write this as like some p mu acting on this as 0. And so we would say that there's a level 1 null operator in this current multiplet. So the current is here at the bottom. At level 1, there's a null operator. And the fact that there's this null operator so then we say that the operator is short. And whenever you have a short operator, the dimension of the operator is fixed by the symmetry algebra. So for instance here, if it's a conserved current, its dimension would be d minus 1 if we're in d space-time dimensions. And so this is just fixed by this requirement that this operator vanishes. So, which is to say that if you have a conserved current, you can't have any anomalous dimension. So the dimension has to be exactly d minus 1. And likewise, another example of a short operator is t mu nu. So t mu nu, again, its divergence vanishes, so we can write this as like p mu. This should maybe be some commutator. And so again, this fixes the dimension of this operator. So here we would say that there's a level 1 null operator, and the dimension of t mu nu then has to be exactly d. So this is, in ordinary conformal field theories, an example of what happens also in superconformal theories, that if you have some null operators where some of the descendants vanish, then the dimension is fixed in terms of the Lorentz quantum numbers. So in the case of supersymmetric theories, what we do is, here. So in the case of supersymmetric theories, what we can do is, in addition to k and p, we could write p as q squared and k as s squared. And so we have kind of half of p, which is q, and half of k, which is s. again, so we can have some primary operator at the bottom. And it's annihilated by S at the origin, and then we can act with various different Qs. And when we act with the Qs, we'll get something where, so this primary operator here, we're going to include also all of its descendants under the ordinary conformal group. And so here, when I write some primary operator, it's really primary operator plus ordinary conformal descendants. And here, when I act with Qs, also we'll get some operators modulo ordinary descendants. So if we look at the supersymmetry algebra, we have something like some supercharges, which are some spinor representation. I'm using kind of 4D motivated notation, but here I just mean something very general. We'll have some spinor, some other spinor, maybe some R symmetry indices. And normally we would say that these things, as I commute to give P mu, here I'll just write that they, as I commute to give 0 modulo conformal descendants. So the idea is that we want to, when we write down these multiplets, each operator in a multiplet is really that operator plus all of its ordinary conformal descendants. And so we can just study Qs that anti-commute modulo ordinary descendants. And, okay, so here we kind of know how it should work. That if we had it, for generic long multiplet, we'll have, we can act with Q, and so I'll write it like this. We take anti-symmetric products of Qs, and here this L can be 1 up to the number of supercharges. So here, these are the number of supercharges. So for instance, in 4D n equals 1, 4D n equals 1 has 4 supercharges, and so the generic multiplet we can act with, well there we can call them Qs and Q bars. So we can act with 2 Qs, up to 2 Qs and 2 Q bars, and that would be what we would say is a generic multiplet. And I'll write it here, so generic. So in the generic long multiplet, we have the superconformal primary at the bottom, and then there's some operator at the top. Q to the NQ of. And these representations of the superconformal algebra, they always have some operator at the bottom, which we can choose there to be a unique operator at the bottom. It might be in some representation of the Lorentz group and some representation of the R symmetry group, so it might have some multiplicity because of that. But we can choose there to just be one operator at the bottom, and then there's also one operator at the top. And it looks like this diamond because when we take this wedge product in the middle, we'll put more operators. So as we act with the Qs, we can get a bunch of different operators, and then there's this operator at the top. And this operator at the top is what we were interested in for this classification of deformations of superconformal field theories. Because if there's an operator at the top, then if you act with another Q, you get 0 up to a total derivative. And that's something then that you can deform your Lagrangian by. So this would be supersymmetric Lagrangian deformation. We're not assuming that the theory is Lagrangian or anything, but I just mean that this is some operator that if you could somehow define the theory, you could imagine perturbing the theory by this operator, and this would give some flow, and that that operator might be marginal, it might be relevant, it might be irrelevant. Typically they're irrelevant, so most of these are irrelevant. Like for instance, if you look in 4D, n equals 1.
So that may be my ignorance. So if you don't have a Lagrangian, what is to deform the theory?
Conformal perturbation.
Yeah, so the first thing you need to try is conformal perturbation theory.
So you would like study correlators and you would try to understand
At least
how
close to,
correlators.
at least close to the, yeah, close to theory, you can do conformal perturbation theory in that one. So for example, if we look in 4D, 4D n equals 1, this would be, for instance, a D term that we can deform by. So in 4D n equals 1, we can act with q squared, q bar squared, acting on some operator. So we have some operator at the bottom, and then we can act with q squared, q bar squared, which is like integral d4 theta. We can write this in superspace, and this would be a D term. And now we come to unitarity. So if we want these representations to be unitary, we have some notion of inner product on them, and we can require that also that all of the operators in the multiplets have a non-negative inner product. So we want unitary. The superconformal algebra, whatever algebra we're talking about on this list. So there's some notion of an inner product from the 2-point function. We want this thing to be bigger than or equal to 0. And we want also all of the descendants in the multiplets to satisfy this. And if, let's say we have some q to the L, q to the L. If that's 0, then this q to the L, back down that L would be 0. So if this norm is 0, then we set the operator to 0. And this would be what we would call an L operator.
More generally, it's a matrix condition, isn't that right? That you may have a bunch of...
That's true, yeah. So right, so at a given level, or a given operator dimension, we might have a whole bunch of operators, and then we want that matrix to have, well, if you diagonalize it, all the design value should be and so this unitarity puts restrictions on the dimensions of the operators. And so, for example, in this case of 4D n equals 1, you can show that all of these D-term deformations are irrelevant.
So is it obvious that you can find all your null operators just among the Q descendants, or do you also have to worry about whether they're also conformal descendant, P, mu? Do you have... could there be null operators that appear only?
Yeah, there could be. Yeah, there could be null operators. In practice, if there's a null operator, like for instance here for these conserved currents, when you complete this to a super symmetric operator, there are also Q descendants which also vanish in practice, and so you can see it just by looking at some Q descendants,
but there's not a... That's always the case, or that, in other words, that you can find them just by looking at your Q descendants of the primary.
I think it's always the case. Yeah. Yeah,
Isn't that just associativity, that the anti-commutator of two Q's is a P? So that means that P commutator J can be written as Q anti-commutator with something?
Yeah.
Right?
Yeah. I mean, here
Yeah.
we're already sitting to 0. We're already kind of ignoring what are the the descendants because it, yeah, basically, I mean, you could wonder if, for instance, here this current JU is some Q descendant of some primary operator, and that operator has its own Q descendant, which is 0. But there's also some other Q descendant that you get that is a conformal primary that's also 0. As far as I know, yeah, at least offhand, I think that all of the operators that contain short primary operators also contain, I mean, short operators of the ordinary conformal group also contain short conformal primaries. That also contain conformal primaries that you obtain from Qs that are also 0. Okay, so if we look at this condition for unitarity, then in all of these different cases, there were the conditions on the dimensions of the operators were studied in various papers that predated ours. Among them, I'd especially liked a paper by Shiraz Nawala that studied all of these different theories and different dimensions and wrote down the unitarity relations. And maybe just right here, the picture of how it goes. So if we apply unitarity, what we can do is so as a function of the dimension of the operator, there's some, let's see here, if the dimension is big enough, then we can form operators that are long representations of the conformal group. And then there's some threshold, let's call this delta A, where some descendant is 0. So this is a null operator. And this delta A takes the form, it's some function, let's write it like this. There's some function of the Lorentz quantum numbers. So these are like the spins of the operators. And then there's also some other function of the R-symmetry quantum numbers. And then there's some offset, let's call this delta A. And just to give some examples, in D equals 6, this delta A is 6. And so, and these functions here are positive also. So for instance, in D equals 6, we can already immediately see that all of these long operators are irrelevant, even before we apply unique because this dimension of 6 is already kind of would be marginal, and then we're adding stuff on top of that. And so these are all going to be irrelevant.
So this is strict inequality?
So this is the dimension where we first had some null operator. And so the long operators have to have dimension bigger than that. So let's
You're saying, are F and G strictly positive or just non-negative?
That's all.
Oh, yeah. Sorry. Yeah, these can be 0.
They can.
Yeah, they can be 0.
So the long operators may include marginal ones.
If the stricter larger than the stricter larger than
Yeah, I'll mention more in the 6-dimensional case, but in the 6-dimensional case, yeah, and this is the dimension of, I should say here, this is the dimension of the operator at the bottom. a multiplet.
Oh.
And so to get a supersymmetry preserving operator, we would have the operator at the top of the multiplet. So we have to add some Q's on here. So even if this thing here had been marginal, we would have to get a supersymmetric operator. We would have to apply a bunch of Q's. 8 Q's, for instance. Okay, so this is what happens for generic Lorentz spins. And then what happens is that if you set some of these Lorentz spins to 0, then there can be, so here it's not unitary. But then there's some special value of the dimensions of the operators where you set some j's to 0, then you can again have a unitary operator if the dimension is exactly that. So there's this kind of gap, and then there's a new set of unitary possibilities. And depending on what dimension we're in, we can have different numbers of these. So for instance, in 4 dimensions, we have both Q's and Q bars. And so maybe I'll just write here our notation. In 4 dimensions, we would label an operator by its left spin, its right spin, it's called a J bar. And then there's some R symmetry quad numbers. This could be, for instance, like the representation under SU2R, if we're talking about coordinate equals 2. We could also include like the U1R symmetry charge. And then there's some dimensions. So this is how we generally label the operators, is that we have Lorentz, the Lorentz taken indices, the R symmetry taken indices, and the dimensions. And so in 4 dimensions, what we can do is we can set either J to 0 or J bar to 0. And so if we set one or the other one to 0, we can have something like this B case. We can actually, in 4 dimensions, have it both left moving and right moving, like B's and B bars. And so we can have, for instance, a long operator for one side and a B bar operator for the other side. And this is the kind of notation that we use in 4 dimensions instead of this Dolan and Osborne notation, but just to make it look more uniform among the different dimensions. And so we have long A, that's this one that's right at the threshold, long, and then B. And then, for instance, in 5 dimensions, SO, if we look at the Lorentz part of the group, we have an SO5. And so there are 2 Dayton indices. And so there are 2 things that we can set to 0. So not only do we have this B thing, we set 1 to 0, but there's another, so again here there's a non-unitary. And then here, there would be another series that, C, where we set 4 J's to 0. And in 5 dimensions, that's it. But then, for instance, in 6 dimensions, SO6 is SU4, and so there are 3 different Lorentz spins. And so you can set up to 3 things to 0. And so this is what you get the A for generic spins. If you set 1 J to 0, you get B's. If you set 2 J's to 0, you get C's. And then if you set 3's to 0, you get D's. So this is where all J's are set to 0. So it's not unitary except for at this special value. So this is what the representations look like. And people who study the superconformal index study a lot, for instance, the recombination rules that you can have. And so these recombination rules are, for instance, something that's here in an A multiplet. Some different A multiplets can combine to give a long multiplet.
Sorry, so it's unitary only on these lines that you draw, or also the lines are not unitary?
The line is unitary, so here this is unitary.
Those are non-states, right?
Yeah, so all of these ones, so in general what we have are, yeah, so for instance, if we look at, just to make it more concrete, if we look at d equals 6,
You drew them as lines, but their positions depend on also the R symmetry, choice of R symmetry.
that's right,
So
yeah.
they're really discrete.
Yeah, there's some. Yeah, so for instance, for 6010, this, let's copy this down. Okay, so for 6010, these are the different spins of the operator. So here we would say that an operator like this with J1 equals 1, J2 equals 0, and J3 equals 0. This is like the 4, if we think of this as SU4.
So what you call spins are the linking labels?
Yeah, these are data labels. And this is, for instance, the 4 bar,
And the 6.
and this is the 6. And so in general, if we had general J1, J2, J3, this function of the spins is a half J1 plus 2J2 plus 3J3. The J1 and J3, the 4 and the 4 bar, are different because of how we choose our Qs. So we choose our Qs to be in the 4. And then this G of R.
So F counts boxes? What is it?
Yeah, F counts. So J1 is, so if we were to draw it in terms of boxes like this. Yeah, so we'll say that there are J1 with one of these, J1 with one of them, J2 with 2 of them, and then J3 with 3 of them.
And the half is just the number.
And we're choosing these, we choose these J's to all be integer, and then this half is, this half is just what you get from
I see that.
looking for where there's a null operator. And then this G of R is 2R, where here this R is, there's, for 1, 0, there's an SU2R symmetry. And this R is the Dictum label for that SU2R symmetry, which we choose to be an integer. So R equals 1 would be the fundamental. And this delta A, B, C, and D is 6, 4, 2, and 0. So for the A multiplets, the dimension, so here this delta for A, B, C, D, we get like this. And the B multiplets have J1 equals 0. The C multiplets have just as J3 equals 1.
So there are no null states, special null states if you just set J1 equals 0, not say J2 or J3.
If you just set
J1 to 0 and not J2 and J3. Is that the?
That's right. Yeah. Let's see. Okay, so what is this? Yeah, so for the long multiplet, it looks like this kind of a diamond. And if the number of operators, let's say here that so the primary operator in general will be in some representation. Let's see right here. So the primary is in some representation of the Lorentz group, some representation of the R symmetry group with some dimension, operating dimension delta. So the number of these primary operators will just be whatever the dimension of this representation is times the dimension of this representation. So that's the number of operators at the bottom. And then the full number of operators in the full multiplet we would just get by acting with these different anti-symmetrized Qs. And so we know that there's going to be 2 to the NQ such operators. And half of them will be bosonic operators, half of them will be fermionic operators. And so for the generic operator, this is what the multiplet looks like. Now, what happens for the A multiplet is that there's some null operator. So here this is this would be O at the top if it's a long multiplet. And if it's an A multiplet, what happens is that there's some null operator. And then we need to set to 0 all of its descendants, that operator and all of its descendants. And so what we get is that there are all these null operators, and then what we're left with is the short multiplet.
It lives on the boundary, this diamond?
I wrote it like this just because this is what you get by acting with some Qs, and then you can act with some other Qs.
So in general, it will live at some point in the middle, and then you need to take it to.
Yeah. So some particular combination of Qs annihilates this one, and then you set that to 0, and then you act on it with all of the other Qs and set those all to 0. And so the idea of recombination.
Going back to your notion of B, C, and D, can you have that J2 is equal to 0 and J3 is not 0?
He says there's no null op.
Yeah.
No short multiplets with that special for that pattern.
Yeah. So you get special ones when you set special choices of these J's to 0. But if you set the other ones to 0, you don't get anything special.
Okay. So that is this easy to understand, or it's just something powerful?
Yeah. When you look at I don't have a fast explanation, but if you kind of look at how what the norm of the operator is in terms of these different spins and how the supercharges act, what you find is that the null operators you always get by kind of making the Lorentz representation kind of smaller and the R symmetry representation bigger. And it kind of just works out that if you set these guys to 0, like because here we took Q, the supercharges Q to be in this representation, then if you set this one to 0, something special happens. If you set the other one to 0, it doesn't.
With this aim of flat, suppose that someone is some aim of flat with a given angular momentum in r class, then can you identify the location of the null thing in the diamond of this null sphere? Something like you can take a touch determinant?
It's kind of more straightforward than the cast thing. Yeah. Yeah, you can just write down what it the so all of these things are done. You start off with some called primary, and with its Lorentz and R symmetry quantum numbers, and then if there's a null multiplet, there would be some Lorentz of the null, and R of the null, and delta of the null. And these things can be read off just fairly easily from the algebra.
So I have a silly question. I am used, I guess, to the notation of Dollar and Osborne, and they have these operators in the A series, B series, C series, etc., with arbitrarily high SOD spin. And of course, their dimension is very high too. So are we saying that these operators are not unitary, or?
No, they'll be a long.
No.
The Dolan
of B series.
Yeah, the Dolan and Osborne ones, they're studying these unitary ones, and so they're
So if you have some operators, let's say, with dimension, I don't know, 6 plus L.
right. So there it's because they have because it's in 4 dimensions. If you think of SO4 as like SU2 times SU2, there's both a J and a J bar.
Yes.
And so then what happens is that you have this description with L and A's and B's for both the left movers and the right movers.
But I am asking whether is your claim that these operators with very high spin are not unitary?
They are unitary, yeah.
So are they long? Because the dimension is very high.
Yeah.
Oh, so that depends on it.
But it's because of this F of J. Yeah, so it's like
increases with L. Right.
So his diagram's a little misleading. Those lines are a bunch of points, and they go off up into the.
That's right. Yeah. So here, if I were to plot as a function of spin, they should be kind of slanted.
Absolutely. Great.
Because so as the spin goes up, these things. Yeah, I should have written these as a function of spin, kind of increasing.
So they are nice, unitary, and short.
Yeah. So those different Dolan and Osborne representations are maybe. You could set one of the J's to 0, and then you get like a B for that side, but then the other one, J bar, is non-zero. Okay. And then, so then it's like there's an F of J and an F of J bar.
Sorry, not all of them are unitary, like for instance, B multiplets, not all of them are, it depends on some. Like in the notation of the Osborne sum, the B are not unitary, in general.
Okay, I have to translate their notation to the notation I like. But yeah, in the notation that I like, if their dimensions satisfy this condition, then the analog of this condition in 4 dimensions, it'll be unitary.
Maybe after you do this recombination thing, after recombination, because if you have, I need to think of it.
I think that on Osborne uses non-unitary ones instead of an auxiliary tool, but if you eventually get a nice distance unitary, you just will representations of the superconformal.
Yeah, that's right.
Sure.
Yeah.
Non-unitary ones, that's an intermediate step, of course, I don't have to do that. If you are more superconformal, and most formal, you don't answer the list. Summary is done on Osborne, right? You're not doing
Yeah, in fact, maybe this ties in with something I was going to mention. So if you look at these A multiplets, what happens is that the null multiplet, the A multiplet itself is a unitary representation. Because that null multiplet knows that it was kind of right here, and it knows that it could have combined with some other A multiplet to become a long multiplet. And so for these A multiplets, it's always like fairly straightforward to subtract off the null multiplet because it's itself a unitary representation. And But then if you look at some of these other ones that are separated by gaps, like these B's and C's and that, their null multiplets are much more complicated. And so they do form some representation of the superconformal algebra, but they're not a unitary representation. And so I think that's what Dolan and Osborne at some point were doing, was they were looking at the null multiplets of these ones that are separated by gaps.
Just one small question. So here you consider only level 1 norms and condition from I think there's only one as far
I don't think so.
delta A.
Right, so actually what happens is that when you look for generic Lorentz quantum numbers, it always happens that for generic Lorentz quantum numbers, the null multiplet turns out to be at level 1. That's, I don't, maybe there's a nice proof of that, but this is just how it turns out. But then as you start to set some of these Lorentz quantum numbers to 0, the null multiplet jumps up to a different level. So, and that's in fact also how you get these other multiplets. So, like for instance, in 4 dimensions, if you set some j to 0, then what you find is that the null multiplet jumps from being at level 1 to being at level 2. And then that ends up how you can get this B representation. And so, yeah, so for generic Lorentz numbers, it's at level 1, but then it definitely jumps up to different levels. So there's some very intricate story, and in our multiplets paper, it turns out to be pretty subtle actually to subtract off these null multiplets in general for not. So for the cases of A multiplets, or for the cases where the null state is at level 1, it's kind of straightforward. But for the cases where the null states are at higher levels for these other multiplets, you know where the null operator is, but there isn't really a straightforward way to just subtract them out. And so
You just, because of the mixing at a given level of all, just finding a basis, is that
it's
the
kind of
point?
just the group, yeah, it's just the group theory problem of writing the supercharges as being in some representation of the Lorentz and R symmetry quantum number. And then it's kind of like you really want to write down what the descendant is in terms of its full Clebsch-Gordon decomposition of all those coefficients, and then there can be various accidents. And so there's a shortcut to the Clebsch-Gordon procedure called the Rocket-Spicer algorithm, which gives a nice way to kind of shortcut having to actually write out all those coefficients. But in some cases, it can be a little bit misleading, and it can, in some cases, you have to be more careful with this Rocket-Spicer algorithm to subtract off proper null states. Like, you don't want to subtract off the same thing twice or things like that.
But it's just a counting problem. And if all you were doing was counting the states, the counting of the short multiplet is just the naive one of taking the counting of the long one minus the counting of descendants of O null. Is that the?
That's right. Yeah. So that's what it is. But in some cases, it can end up being kind of surprisingly subtle or complicated just because of the group theory. So we had this long multiplets table where in the end, we had some algorithm that seemed to work, and that we believe works in all dimensions. But we kind of just presented this algorithm as a conjecture because we don't really have the proof that this is the right way to do it. But it seems to satisfy many different checks, like this recombination rules and the correct Bose-Fermi pairing. And it reproduces kind of all of the known examples. So the multiplets story, in the end, it's straightforward for the long multiplets, and then for the short multiplets, it's kind of, there were some surprises. And just to mention some of the different, check the time. So there are various curiosities in terms of the multiplets. And so just to name a couple. If we think of these multiplets as animals, then it's like the thing at the bottom is its foot, and then we're looking for the operator at the top, which is like its head. And so there are some multiplets with multiple heads. And some of these are kind of well known. Like for instance, in 5D superconformal field theories. If we look at the conserved current multiplet, so this is, in our notation, the way we would write the conserved current multiplet. These are the Lorentz quantum numbers of the operator at the bottom. So it's a Lorentz singlet. Its dimension is 3. This 2 means that under the SU2R symmetry, it's an adjoint. So this is like the moment map operators at the bottom of conserved currents in 4D equals 2. And this is in the C short multiplet, and this 1 means that it has a level 1 null operator. And so if we act with yeah, so maybe I'll just write here a bit.
What are the possible levels for the null operators?
So in this case, the null operator is at level 1. And yeah, so if we write down, let's write like this. So this is 3 operators, 3 scalar operators, because it's in the triplet of SU2R. And so let's just write here. This is 3 operators, and then there are 8 supercharges. So in general, we could have gotten 24 operators here. But in the end, we only get 8 operators here. Let's say this is 3 bosonic operators. Here we have 8 fermionic operators. And these 8 fermionic operators, this is one. This is in like the 4 of SO5. So this is in the 4, and then this is a doublet under the SU2R symmetry. So this is 8 operators. And so this is at level 1, and so the fact that we didn't get 24 operators here at level 1 because we had 3 to begin with and we act with the 8 Qs is because the other ones are set to 0. So this means that at level 1 there's some null operators. And then if we go to level 2, so this is acting with Q, then we get and so these are the conserved currents. This is in the 5 with the Lorentz group. And so this is under the Lorentz group of 5, but actually because it's a conserved current, it really counts as like 5 minus 1 because there's a conservation law. And so we can see already that just Bose-Fermi matching wouldn't allow this, so there has to be another operator here. And so this operator here is just a Lorentz singlet. And so this would be an example of an operator with 2 heads. There are 2 operators at the top, which are both the top of the multiplet. One is the conserved current, and then one is a scalar operator, R symmetry preserving scalar operator. And this is actually, this operator has dimension 4, so it's relevant, and it's at the top of the multiplet. And so this would be a relevant deformation. because it's dimension 4, its coefficient would be a mass term. And so this would be like if you have a 5D theory which has a conserved current, that conserved current always has kind of an associated mass terms that you can add. And so this is another thing about 5D superconformal field theories, is that you can have mass deformations associated with global symmetries. And actually, these are the only relevant operators of 5-dimensional superconformal field theories, it turns out. So when we went through our list of all of the operators, this was the only one that was an operator that was relevant. There are lots of irrelevant ones, of course, but this is the only relevant one that's supersymmetry preserving. Am I supposed to stop now? Please. Okay.
One question. Up to now, you told us about null operators at level 1. You didn't mention any others. So what are the options that you have?
Yeah. So as yeah. In fact, I was about to mention another. Maybe I'll just say before the break. Just to give another example, the stress tensor multiplet in 5 dimensions. The stress tensor multiplet, so this contains, these are Lorentz scalars, they're singlets under the R symmetry. This is the bottom of the multiplet, it's dimension 3. And then once you get on 2 Q's of the 4th, there's T using. So and this 2 here means that this is an operator whose null multiplet starts at, whose null operators start at level 2. And the fact that this is at level 2 is kind of the fact that that there's a B multiplet and that it's at level 2 is tied to the fact that these are Lorentz singlets and also the fact that there are charges small.
Are there examples where there's more than 2 null conformal primaries in a given irreducible supermultiplet?
No, it's always, it turns out to always be a unique operator.
Just
the one exception to that is in these cases, like in 4 dimensions where they're separate left-moving and right-moving ones, then the null operators, you have like separate null operators for the left-moving piece and the right-moving piece, and then when you tensor them together, there can be multiple ones. So like when you look at these recombination rules in 4 dimensions, you see that it's not just one multiplet that's combining, but that's just because of the separate tensor product of left and right.
Right. So can you have a situation where, so the superconformal multiplet for which the null state is the primary could also have null states in it. So that you have nulls, so you have to add those back in. You know what I mean?
Yeah, the null multiplet can have its own null operators, but you don't actually add them.
No, I know.
You
have to kind of overcounting.
Yeah. So there can be things like that where you have to be careful with subtracting them off. But yeah, in the end, it's not.
No, you're not adding them, but that's bad nomenclature. But yeah.
Yeah, that can happen.
You should subtract them twice, right?
That's right. Yeah.
So in 5D, it's relevant to singlet operator. That's like Yang terms or what?
This visual operator.
It's a mass term.
These are like mass terms.
Something like that, by problem.
Another example of this would be also if you had a gauge theory that you start so there are these 5-dimensional superconformal theories that have a relevant deformation to a gauge theory where 1 over g squared plays the role of a mass. And that's also of this form because there's this topological U1 that you can get by utilizing F wedge F to get a conserved current. And that conserved current also is of this form. And so this operator here could be, for instance, like the Yang-Mills coupling. Or this could be like, for instance, F mu squared. This dimension 4 operator could be like F mu squared, and its coefficient is like a mass term.
Or it's local operator, unique.
Well, so this thing ties them with global symmetry currents.
Okay.
And so So one way to say it is just, if you know the global symmetry of your 5D theory, then you know all of the relevant operators, because all of them kind of come together by supersymmetry. They're all tied together with global currents. Yeah, the next thing that I was going to say, which maybe I won't say it after the break, so I'll just briefly mention it now, is that if we look in 3 dimensions, there's some really bizarre multiplets where there's like a head sticking out of the middle of the body. At least in this case, the two heads were kind of at the same level. But in 3 dimensions, there's some ones where like the head is kind of sticking out in the middle. And so there's some supersymmetry preserving operators in the middle of the multiplet in 3 dimensions.
Can you give example?
Yeah, so for example, like the 3D n=4 stress tensor. Actually, the stress tensor for n is 4 or more in 3 dimensions has, the stress tensor is at level 4, and then there's a level 2 operator, which is a Lorentz scalar, and so you could add it to the Lagrangian, and it's like a mass term, and it's just there in the middle of the multiplet for any theory. And so these are some mass deformations that you can do of 3D theories with n=4 or more. And
It's not associated, as I see.
And not
There's no
associated.
global symmetry associated with that, unlike this other.
yeah, it's there in the stress tensor multiplet, and so it's actually related to this non-R. It's related to this kind of central extension, special central extension that you can have in 3 dimensions. Where, yeah, non-central terms where you use the R symmetry instead. And so it's related to that.
Topological symmetry.
No, it's not.
Under all this global symmetry.
Mhm. Okay. Yeah, you have to look at the global symmetry. That would depend on the theory. You kind of look for what I call circumference.
Because you can turn only one family term, and the rest of them should be like random. So, for example, as it is 5 flavor, there's E6 global symmetry, then you can turn on relevant information only for simple Yang term, then rest of that is the high terms. You can choose from any one of them to be Yang and one. So there's some strange.
Yeah. So for in that case, you have to use the fact that the conformal field theory has this bigger exceptional global symmetry, and then you can kind of choose some Cartan direction or like in there.
So some of conformal symmetry is imposing some has to be Yang, some has to be best on.
So yeah, I mean at the origin there's this bigger symmetry that comes from when you move away from the origin, then I guess you can see this distinction. Okay, so I thought for the second part I would change gears and talk about these connections, well, especially the 6D case and the connection between conformal anomaly A and these isotope anomalies. So maybe just as a warm-up, I'll review some things about the anomaly polynomials. So you know, in even space-time dimensions, we form a D+2 form, which gives the anomalies. And in general, this D+2 form contains anomalies for gauge symmetries. If the theory is sick, in general, you have to cancel the gauge anomalies and global symmetries plus gravity pieces. And when we're kind of studying these properties of flows, a very useful, so this is for D even. A very useful properties of these flows is a Topf anomaly matching. which says that if I look at the piece here involving global plus gravity, these terms are constant along RG flows. And more generally, they're constant along any kind of deformation of the theory that preserves the symmetries. And maybe just to remind people, from this d plus 2 form, we write it as d of a d plus 1 form, and it's usually written like this because it's 0th order and some gauge parameter, and then the variation of this d plus 1 form is d of a d form, which is first order in the variation. So this would be like the gauge parameter if we're doing a gauge transformation. And the change in the effective action is basically this thing. Sometimes people think factors are too high, but okay. So this is the descent description of anomalies. So for instance, in 4 dimensions, this would be a 6 form, and so we could form a 6 form out of f mu squares, and that comes, for instance, from a triangle diagram like this. And so we can have, for instance, in 4 dimensions, I6 contains some term like C3, some field strength. This is the third class of the field strength. These anomaly polynomials, part of why they're so nice is they're all built up out of topological quantities. And this is related to the fact that anomalies have some topological connections. And here there's some coefficient that would depend on the theory. Let's call this K F. So that would be, if we had a perturbative theory, that would be what we would compute from this kind of triangle diagram. And if the theory, if this F is a gauge symmetry, then this thing has to vanish, otherwise the theory would be sick. But if it's a global symmetry, we could turn on a background field strength for that global symmetry, and then this is an anomaly coefficient, and then we would say that this is an 't Hooft anomaly. And 't Hooft's argument is that this is constant along RG flows, and so that's incredibly useful for trying to figure out where the theory ends, because for instance, if it's not zero, that tells you that the theory can't end in a mass gap theory, with a mass gap, because this thing only gets contributions from massless fields. And so, okay, so this is kind of just to sort of remind people about some of these anomaly coefficients. In 4 dimensions, we can also look at things like KF, C1, F, P1 of T. This is a Pontryagin density. This is basically like if we turn on a background curvature, this is R times R dual, and then this would be basically just F. This is allowed if the theory is U1. So if there's a U1 symmetry, we can form just F. And otherwise this thing wouldn't be gauge invariant. And so if we have a U1 gauge symmetry, we could try to we would want to set this thing to 0. And again, if this is a global symmetry, this tells us that we could look at a triangle diagram with a global current at one side, and then we could think of these as background gravitons or background stress tensors, and then this would be like the trace F 't Hooft anomaly. So these are the form of the 't Hooft anomalies.
So if there's a U1, there could also be a C2 times C1?
Yes. Yeah. So we can also look at things like C2 of F, C1 of G. Let's suppose that F let's suppose that F is abelian. So you would form like C1 of F.
There's also a C1 cube.
And a C1.
G, yeah, we can form C1 cubed with some coefficients. And what else do I want to say? Let's just leave it at that. Yeah, so we could also form things like this, where with different, where F and G might be different symmetries. And now, if, for instance, if F is a U1 global symmetry, and if G is a non-abelian gauge symmetry, then this coefficient would be like, for instance, the coefficient of the axial anomaly. So this would tell us, for instance, that some U1 axial might be anomalous if this coefficient is non-zero, and then we would just say that this U1 global symmetry is violated by instantons in that case. So that's the case if F is global and G is gauge. On the other hand, if you consider the case where F is gauge and G is global, so here we go right here with F is global, G gauge. This is called the ABJ anomaly. This tells us that if we look at a global current at one side of the triangle and gauge fields at the other, we get something non-zero, which tells us that an instantaneous charge under that. On the other hand, if F is gauge and G is a global, this is what I would call an example of a mixed anomaly. And the distinction that I want to make between these two cases is that in this case, okay, so this is a triangle diagram. It's right here. This is a triangle diagram with F at one vertex and G at the other vertices. So if G is a gauge symmetry, this just tells us that this global current has a non-zero divergence. So du J axial mu is proportional to F dual. And that tells us that this...
Or the other way around, GG dual.
Oh, yeah, GG dual is called. So that tells us that this global symmetry is broken. On the other hand, in this case, what this tells us is that if we turn on some background fields, the background fields kind of violate the gauge symmetry. Or in other words, if we turned on a configuration of the background gauge fields that look like an instanton. So the G instanton configuration is U1 charged. And that can happen. For instance, if we just look at QED with massless fermions. So if we looked at a U1 gauge theory, so if we look at 4D U1 gauge theory, we don't even need it to be supersymmetric. Let's say that we have NF Dirac fermions. So then there's an SUNF. If we write the Dirac fermions as chiral fermions, there's separate SUNFs that act on both the left and the right pieces. And we could look at the case of U1 gauge SUNF left, SUNF left. this triangle diagram is non-zero. And so this would be an example where this anomaly is non-zero. And so this is a mixed gauge. Gauge global anomaly. And so one thing that I'll argue is, okay, so just to say what part of the reason why I'm discussing all of this is that I'll argue that, for instance, in 60, 10, QFTs also have such anomalies. Similar mixed anomalies. And an example of this would be the small SO32 instanton quantum field theory. Here I'm writing quantum field theory, not conformal field theory.
So, in 60, of course, it's box diagrams rather than triangles. And
That's right. Yeah.
so I mean, how does your sort of more refined nomenclature adapt to the 60 case? So in 40, if you had one vertex which was global and two vertices which were a gauge, we called that ABJ, and if it was the other way around, we called it mixed. What's the nomenclature for for 60?
Yeah. So, actually, you're reminding me. I wanted to say that this is associated in perturbation theory. We would say that there's like a D plus 2 over 2 gone for that diagram that we're talking about that leads to these anomalies in D dimensions. And in general, I'll say that the analog of an APJ anomaly is where there's just one global symmetry and everything else is gauged.
Okay.
And then the analog of these mixed anomalies is that there's two or more global symmetries. So the global, if there are two or more global symmetries in the anomaly term, like background gauge fields in the anomaly term, it means if you turn off the global symmetry background field strength, the current is at least conserved.
Right.
Like here, in the ABJ case, the current is just violated. But in this case, if you turn off the background gauge fields, the global current is, or in this case, the gauge symmetry is conserved. And so I'll make a distinction between if there's one field strength or more than one field strength. And so I'll mention that there are these similar kinds of mixed anomalies in general at 6 dimensions, but they're not there. But not in superconformal field theories. I'll mention about how this follows from the classification of operators. So there's from the operator. So this is one kind of physical consequence from the classification of operators. Actually, maybe I'll say right now how that works.
And this mix just refers only to the gauge global or also to gravity global?
So you could have like P1 and
gravity and global too.
Also.
Yeah.
Okay.
Yeah. So this is an application of, if we look in 60, so if we look at 60 conformal field theories and whether they're very short multiplets, among the short multiplets, thinking about these as SU4, SO6, Lorentz as being like SU4, and writing down the spins of the operators. If we look at operators whose spins are like this and whose dimensions are a half J1 plus J3 plus 3, these turn out to be all allowed short representations, unitary short representations of the conformal group. And as a special case, if we look at J1 equals J3 equals 1, this operator we could think of as being J mu nu, where here mu nu are Lorentz indices and are symmetrized. So this is like a two-form. And it's conserved. So if we have this dimension, this is in fact the null operator that we have. So this thing has to be set to 0. So it's like a two-form version of a conserved current. And it turns out that this can't exist in superconformal field theories. If we look at our full list of operators and multiplets in superconformal field theories, there's no multiplet that contains this operator. And so this tells us that in a superconformal field theory, you'll never find an operator like that. And and its dimension, we should sit here also. So in this case, J1 and J3 are 1, so its dimension is 4. And now, if we suppose that we had a mobile symmetry.
So this current for strings?
Yeah, this is like a string current.
So if I have a little string theory, then it's okay to have that?
No, that's a self-dual current. This is just a two-form, without any such constraint.
Yeah,
But you could impose the constraint.
a two-form, two self-dual and anti-self-dual two forms are like 2, 0, 0. These are things where it's like a 3 form with a self-duality constraint. So this would be like the field strength for a self-dual. Yeah, but this J mu nu is the thing that we would want to couple to a B mu nu. And so, but it doesn't exist.
I didn't understand the answer. So what about little string theories? You're just going to tell me, well, they're not actually a conformal field.
No. There are short superconformal multiplets which contain those guys.
Yeah.
There aren't short superconformal multiplets which contain this guy.
But
I was still looking for a current, that's all.
Yeah, like for
not
instance,
a field string. I wanted something that would
like for instance, if we look at a free tensor
multiplet.
multiplet in 6 dimensions, so a free tensor multiplet would be in this notation something like this: 1, 2. So this is a hypermultiplet.
So string current has to conserve this one.
It would be some fun. It doesn't have this.
So this will help you later. So this is a free tensor multiplet. And at the top of this multiplet, there's 2, 0, 0, 0, 3. And this is like a H mu nu row. So this is like a field strength for a self-dual. So this is a tensor multiplet, but what you see is like the field strength for that, which is like this 3 form with the self-duality constraint. And this is in this representation of the Lorentz group. So this one you can't have. But it's this kind of conserved current that was naturally coupled to a 2 form. It turns out it isn't there. It could be there in a theory that's not conformal, like a little string theory. Yeah. Okay, so one consequence of this is that if we look at some global symmetry, and if there's one of these mixed anomalies, suppose that there's a suppose that I8 contains a term which is like C2 of F, C2 of G, where maybe F is a global symmetry and G is a gauge symmetry. So then, this C2 is like F wedge F. So this is a 4 form, and this is a 4 form, and we get an 8 form. And this has some coefficient, let's call this FGG. So then the divergence of the corresponding global symmetry, let's say corresponding to F, would be this K FGG, a background gauge field for F. Times something which is like this J mu nu, where this J mu nu would be basically like this C2, it's like G rho sigma, G capital lambda, epsilon u nu, rho sigma, capital lambda. So if this kind of mixed anomaly were there, we would say that we should see in the conformal field theory that if we turn on a background gauge field, so we would have a global conserved current, we turn on a background gauge field coupled to that global conserved current, so this is some global background gauge field coupled to the global symmetry, then what we would find is that the current would have an unobserved divergence given by that anomaly. But this F global has to be contracted with an operator, which is exactly this operator, which we can say doesn't exist in the conformal field theory. So this is one application of this classification of multiplets, is that we can show that these kinds of anomalies have to be zero in a conformal field theory.
So the instance of string.
Yeah, that's right. Yeah, so this would be like.
So I'm a little confused about this argument. I mean, if I have a gauge theory, trace of G wedge G is a gauge invariant operator, and all you're telling me is that it's not part of a superconformal multiplet.
Right. Yeah. So we can.
It's not. It doesn't have definite scaling dimension or something in a supersymmetric theory. Is that the statement you're making?
Yeah. Yeah. It sounds like a very strange statement, because you would think if you write down a gauge theory, surely you could write down this operator, and we should find that operator somewhere in the spectrum of operators.
Well, I mean, it might not have definite scaling dimension, but it's certainly an operator.
It is an operator. Yeah. So what we want to argue is that actually it becomes part of the long multiplet.
Okay.
It looks like it should have dimension 4, and it looks like from that it should have a short multiplet.
So this was my question. I mean, the operator's there. It doesn't have the dimension you might have thought it ought to have. But why does that imply that the equation you wrote doesn't make sense?
It doesn't.
I mean, that term couldn't have appeared in the anomaly, right? I'm missing something in the.
Yeah. So actually. It's kind of like this operator classification knows all sorts of things about conformal field theory that have to work out. And the way that this actually ends up working out, I'll kind of discuss a little bit more how this actually ends up working out, is that if there is a gauge field, like here this involves some gauge fields.
Right.
If there is a gauge field, then in general we have to cancel the gauge anomalies. And so to cancel the gauge anomalies, first we have to make sure that there's no irreducible gauge anomaly.
Right.
And so that determines the matter content.
Right.
But then there's still going to be a reducible part of the gauge anomaly.
Right.
And to cancel that reducible part of the gauge anomaly, we have to do something like a Green-Schwarz mechanism. And it'll turn out that the Green-Schwarz mechanism tells you that exactly this operator has to act as a source for the B field. So here we have to add in a tensor multiplet where now D of this H is going to be related to that. And so this operator kind of isn't anymore a primary operator because it becomes D of this operator. But not only that, this operator has to be something like not a abelian version of this operator. Because if it were just the abelian version of this operator, we would still have an operator with this dimension in the spectrum. And so it's kind of like just this classification of operators knows that there has to be this whole long story with anomaly cancellation and non-abelian two forms. And in the end it works out. But
isn't there a simpler answer to the question, which is the anomaly polynomial has to be closed, so that J mu, if it's going to enter in the anomaly, has to be conserved.
yeah.
And if there doesn't exist in the short multiplet, if it therefore belongs in a long multiplet, it just means it's no longer conserved once you do the flow. I mean, in any 60
No, but it's funny because
field.
you're only measuring its non-conservation in the presence of this background F
Yeah.
curvature.
Yeah, I mean,
Right?
definitely
And I don't, those are, that's a...
No, not the global current. The
Yeah, I mean,
J mu.
definitely everything you said I agree with, but it's like, all I was saying is that if you start off with an explicit example, like some
Yeah.
gauge theory, it might look a little bit confusing why this operator that you could write in that gauge theory doesn't satisfy that condition. And it turns out that it doesn't satisfy that condition because you have to go through this long story with anomaly cancellation.
But sometimes it
Doesn't satisfy.
It's not actually a closed primary operator.
But you can have just abelian tensor coupled to this gauge instance string. So you are saying just DH equal to this instant current, and that makes.
Yeah, I mean, so I'll go through some examples where you can definitely write down in some gauge theory examples some operator that is this operator, but it just doesn't end up being the superconformal. It's not, in the end, it's kind of not a gauge invariant operator because it acts as a source for this H, which in the end becomes part of a non-abelian version of that H.
H doesn't need to be non-abelian if you have similar tensor.
Well, it turns out that that's what the theory is telling. That's what this superconformal classification is telling you. Because there just isn't such an operator that has the right properties to be this operator otherwise. Okay, so maybe, okay, so this is one application of this operator analysis, is that these kinds of mixed anomalies, even though they can be there in general quantum field theories, like for instance in this theory, maybe I'll write down more explicitly what it is in this theory, but they're non-zero, but if you look in conformal field theory, they have to be zero. And this was something that we liked because, so at the very beginning I mentioned that there's this formula that we had for the conformal anomaly A. just to make this formula a little bit more concrete, if we look at a free hyper, I'll just write down some examples. And again, these, when we look at the anomaly polynomial, so there's some factor of 4 factorial. So this is a background gauge field coupled to the R symmetry. And this is the piece involving the pointary eigen density for the background curvature. Gamma t squared. Okay, so this is the notation for these alpha, beta, gamma deltas. And we can write them down in for various different cases. So for the hypermultiplet, it's kind of obvious that these ones are zero because the fermions in the hypermultiplet are symmetry singlets, and so they don't contribute any anomaly here, but they contribute to gravitational anomalies. So this is a free hyper, this is a tensor. These normalizations look a little peculiar, and the reason is because we normalized everything so that A for a free 2-0 tensor is 1. This is just our normalization conventions. And so the 2-0 tensor multiplet we can think of as a 1-0 tensor plus hyper. So if we add these things up, we get 1. So that fixes our conventions.
But there was an additional normalization for the coefficients of alpha, beta, and delta theta.
No, he's going to figure out that he's motivated.
These have some fixed coefficients that you can determine for these theories. For like these alpha, beta, gamma, deltas, for these cases, we can read from the paper of Alvarez, Gomez, and Minute for these anomalies.
Oh, it comes from the geometry, you say?
Yeah, like in these cases, these are just perturbative, and so we can calculate it directly from these formulas that they write for the anomalies that, you know, like it, for fermions, in this case fermions and the self-Dirac tensors. This is something that was in Alvarez. We can do this also for the vector multiplet. And so here we get -1. Just before, just to quickly mention, a free hyper and a free tensor, these are representations of the superconformal algebra. But a free vector is not. In 6 dimensions, anything outside of 4 dimensions, a free gauge vector multiplet is not a representation of the conformal group. And so, so even though it's not a representation of the conformal group, we can still ask whether it's anomalies. And so here we could compute, you know, just from the fact that there's the fermions are in the doublet of SU2R symmetry. We get these things. And here, these pieces we can read out from Alvarez and Gomez. 160. While we're at it, let's just write down the 2-0 theories. With G as an AD group, and then this coefficient is HG, the dual Coxer number, GG plus RG. This is a half RG. 1/8 RG. This is the rank of the corresponding AD group. These are just some examples of this, using this formula.
So
And-
this additive, how do you get the expressions?
Right, these cases here, this was worked out by, so let me just say here, for the 2-0 case, it takes the form of some kg, I think there was a factor of 24. So for the 2-0 case, we can have an SO5R symmetry. And so if we turn on the SO5 background field, we can form P2 of R. This is something we couldn't do in 1-0, where it's just an SU2R symmetry. Because SO5 has a coordinate Casimir, and SU2 doesn't have a coordinate Casimir. So this is the formula for the anomaly polynomial for 2-0 theories, for general background, for the R symmetry, and for the geometric. And this KG.
So this is the pure R. You haven't included any coupling to the background curvature.
No gravity pieces.
The gravity.
Yeah, the gravity pieces are in here.
Oh, the gravity pieces are unmodified from free K. I see, right.
Yeah,
Okay.
and so like, for instance, here, these gamma and deltas are the gravity pieces, and so these...
No, I understand. Yeah, okay, so that's, I see.
And this is the formula for KG. But if we decompose this SO5R symmetry as being like an SU2R symmetry and another SU2, it's called SU2 left global symmetry. And so we decompose it under n equals 1, this is what we'll get. And so we plug it in for all of these different cases. Now,
So how just remind me how that was worked out in the 2-0 case?
Thank you. This question. Right. So actually, so Harvey Magnesium and Moore. So yeah. So this thing was somewhat studied in the 90s, and so Whitten looked at the case of a single M5 brain and studied how there's these anomalies in the world volume of the M5 brains mean that there's inflow into the bulk. And so what Whitten did was to match the inflow of a single M5 brain to the bulk and found that there was a mismatch, actually. And so this puzzle was fixed by Fried, Harvey, Magnesium, and Moore. And they showed not only how to fix this mismatch, but how to compute it for general N. And so in the bulk, you're using M theory. So we can think about this as M theory and 5 brains. And there's this CGG term that you have in M theory. And this CGG term ends up giving an n-cubed contribution to like an inflow in the bulk, which you then interpret as like an n-cubed contribution to this term here. And so there was a term, so what Harvey, Magnesium, and Moore found was that K of the AN cases was n cubed minus n by n inflow, where the n cubed came from this piece in the bulk. And then actually, yeah, so I wanted to mention about anomaly matchings. Maybe here I'll say some kind of, take a break from this and just say some general thing about anomaly matchings. Anomaly matching also must hold place.
No, otherwise, there would have been no Whitney paper to build on.
Yeah. And anomaly matching also must hold on the moduli, well, everywhere on the moduli space. But what can happen is that if we have some scalar fields phi, they can, if we have some global symmetry G, they can break it down to some subgroup H, and then, so we have some pions, which are Mandelbrot bosons, which are in this coset space, and then what happens is that these can contribute to anomalies. Even though they're bosonic fields, they can contribute to anomalies. And not only can they, but they, in general, they must. Because if we want to have anomaly matching. And so this was first studied in 4D, in the West amino effective action, or what's called the West amino Witten effective action for, let's say, QCD with NF greater than or equal to 3 massless quarks. So we have an SUNF squared, which breaks down to the SUNF diagonal. And all of the anomalies have to match, including in these broken SUNFs. And so then what happens is that you need an interaction term for these pions, which matches it. And so there has to be a term, so the trace of SUNF cubed, if we look at the triangle diagram with 3 SUNF pH fields, or the anomaly polynomial, there's a piece which is like C3 of F SUNF. This coefficient is NC. And so to get that NC, what Witten showed was that you have to have a term in the effective action, which is like NC, and then you get it actually like going to 5 dimensions. Let's call it phi star omega 5, where omega 5 is the phi form that you can form on G mod H. So G mod H has a phi form. You pull this back with the scalar fields, and then you integrate that and with the function NC, and then this contributes to the anomaly matching. And so this is the way that it works in 4 dimensions. And then, actually, I studied this theory back in like the year 2000 or something to try to do the analog of this, for this case. Like, for instance, if you go away from the origin on the Coulomb branch of the 2-0 theory, the anomalies are going to look like they mismatch. Like, for instance, we could break AN minus 1 down to AN minus 2 times U1, and then it'll look like there will be a mismatch. And so there has to be an anomaly matching term. And so there's some analog of this in the 6 dimensions case, where it ends up being, instead of this NC, it's like delta of this K, G. So if we go along the Coulomb branch, there's a mismatch in KG. Since we're in 2 higher dimensions, this is 7 dimensions. And here this is some, turns out to be some 3-form, which, and this ends up being related to the fact that I7 of S4 contains the integers. This is the hop, one of the hop maps. And anyway, so there's some long story which helps to motivate this.
And omega 3 is some.
Yeah. So when if you break SO5 down to say SO4. On the Coulomb branch, there's an S4. And so this S4 has a 4 form. And so d omega 3 is basically like the pullback of that 4 form with the scalar fields. So this is an example of how, so these anomalies have to match, and then this tells you that there's an interaction term like this in the effective theory on the Coulomb branch, which is needed to make it match. And it has some specific coefficient. And part of my goal when I looked at this back then was to figure out from this coefficient how to derive this for integrating out some fields, like some massive strings or something. And I don't know a direct way to derive this by integrating something out, but this should be some clue for the theory.
It's still an open problem.
Yeah. Yeah, so one of the things that we can look at now is the analog of this for 1-0 theories. And in fact, if you look at this for 1-0 theories, we have, so for 1-0 theories, we have, so the analog would be that we could be in the conformal field theory at the origin, or we could go in the moduli space. And here there are two components of the moduli space. There's the tensor branch and the Higgs branch. And if we wanted to, just to give an example, we could look at the small E8 instanton theory, where here the dimension in hypermultiplicity units of the Higgs branch is 29. This 29 is the dual Coxer number -1. This is like the number of moduli that you have for an instanton. These are the overall translations that are kind of free decoupled hypermultiple, so you can subtract them out. And then there's this tensor branch. The tensor branch is 1. And the fact that, actually the fact that this is 29 and this is 1 is related to the fact that here these have this ratio of 29 and 1. So that if you have 29 hypermultiplets and 1 tensor multiplet, they have the same value of this delta, where delta is this P2 of T.
That's the DAF computation one, right? This column of delta. Was,
Yeah, that's true. That's true. Yeah, this was, yeah. Yeah, I guess, yeah, in fact, he computed this even before maybe Elvis computed it.
yeah.
Yeah. That's right. Yeah, so that fits with the fact that this anomaly polynomial can be everywhere constant as we move around on the moduli space, because delta is the same for all of them. And so the theory at the origin has, in fact, this same value of delta. It's like minus 29 over 60. But as we move around in the moduli space in general, like for instance, if we grab a tensor branch, it could look like there's a mismatch in the anomaly. So this I8 might be an apparent mismatch between the I8 here and the I8 here. So if they seem to be different, there could be a mismatch. And because of anomaly matching, that mismatch has to go away somehow. And so the way that the mismatch, this apparent mismatch can go away is because on the tensor branch there could be something like a Green-Schwarz mechanism that allows you to match it. And so this apparent delta I8 could be something like I4 squared, where here we have a 3 form. And this I4 can act as a source for the 3 form, And the effective action can contain a term which is like where this I30 is like the thing that we would get from the descent procedure. We write I4 locally as d of I30. And this is an analog of the Green-Schwarz mechanism. And so this leads to a contribution to the anomaly polynomial, which is the square of something, and that square of something can match the anomalies. And actually, this is what led us to this formula on the tensor branch, was by saying that on the tensor branch, there's a real scalar, which is actually the dilaton. And supersymmetry relates that dilaton to the tensor multiplet H3. And on the tensor branch, we can have we can write down some dilaton effective action like this on general grounds. So here, you can look at L-bank. L-bank et al., for instance, studied the way that the dilaton couples in 6 dimensions without supersymmetry on general grounds. So if we kind of expand in the dilaton, we get something like this. And this coefficient.
This is some there is some behavior for the small values of phi.
Yeah. This is from expanding these coefficients where we write down. So we write down this g hat, which is like phi times g mu, to get something that's violent variant, and then we form these combinations of the curvature out of g hat, and then we expand this g hat for small phi, and then we get something like this. And this term is in the list of operators. Oh, is this my cutoff?
You could still
In the area.
Thank you.
Okay, so this is in our list of operators. It's actually of the form q to the 8th. Q to the 8th acting on some operator O. And this one actually isn't in the list. So if we try to form some operator like this, we can't form it. And so that looks kind of puzzling, but the way that it actually works out is that if you do some deformation, you know, like for instance with superpotential deformations, there's a term which is W involving like the second derivative of the superpotential times psi squared, and then there's another term that you get which is like W prime squared. And so if you do the deformation, the deformation itself changes the supercharge, and then you have to iterate that. And so the interpretation is that this comes from iterating this term. And so this actually is from, so it's not, it's actually from the B term. And so the conclusion from this is that delta A is proportional to this B squared, which actually already tells us that this B is real, and it turns out this B has same nice properties that delta A had in 4 dimensions by the Kormatzky-Schwimmer argument. This B is something where you can argue from some spectral analysis it has to be, in any interacting theory it's positive, and the only, it's always non-negative, and the only way that it can be 0 is if you have a free theory. And so this thing shows that this delta A is bigger than 0 if you go along the tensor branch. This delta A is bigger than 0. And actually, this is related by supersymmetry. There was an old paper by Bergshoff and Sezgin and Salam from like the 80s, where they were studying R squared supergravity in 6 dimensions, and by kind of using this analysis, it's possible to see that this is related by supersymmetry to the delta I8 is K I4 squared anomaly.
Was Sanioti aware of this?
Oh, I don't know. Yeah, I'm not sure. So I didn't get to the whole part of my story, which was the part of the punchline for saying about these mixed anomalies not existing in 60. Can I take just a few minutes just to say the punchline? Okay, so there are many theories in 6 dimensions that you get by gauge. So there's no theory with just gauge fields, but there are plenty of theories that you can get by gauge fields and tensor multiplets. And so you can have something like a tensor multiplet, F mu nu, F mu nu. These kinds of theories were studied by various people, but so among them was Seibert. Also, so this is from a tensor multiplet. The basic problem with gauge fields is that the F mu nu squareds, F mu nu wants to have the same dimension 4 and not the same dimension. And so this, we just had F mu nu, it wouldn't have dimension 6. If you multiply it by a scalar from a tensor multiplet, it does. And then if you supersymmetric complete this, there's going to be a term which is like, so this phi has an h, which roughly we can think of as dB. And so there would be a term which is like d wedge f. And this term here is some coefficient. And this coefficient here can be actually used to cancel the gauge anomalies. So this C is some fixed coefficient. And so there are plenty of these 60-1-0 theories that involve gauge fields, matter fields, and tensor multiplets, where you cancel the gauge anomalies by coupling it to the tensor multiplet. And then if you use this formula to compute A of the theory, we would say that A would be minus 251 over 210 times the number of vector multiplets. I'm just using this ring, plus 11 over 210 times large negative thing. And that looks bad for A counting the number of degrees of freedom because you want A to be positive. But there's an extra contribution for A that comes from this Green, Schwartz, West, Sagnani mechanism that we use for anomaly matching. And this thing includes crucially the R symmetry pieces, like R squared, look. There could have been terms like C2 of the H field, C2 of the R symmetry. There could have been a term like that in the anomaly polynomial. And in general, there are terms like this. But because of our argument that such terms can't be there in the conformal field theory, these terms have to be canceled. And these terms can be canceled by some anomaly polynomial, some analog with this Green-Schwartz mechanism. And in fact, this cancellation of these mixed anomalies was already incorporated in this nice paper of Mori and collaborators, where they write down the anomaly polynomial. They kind of just assume that these pieces have to vanish. But when you cancel out these pieces, you get a contribution for A, which turns out to be big enough to make this whole thing positive. So this thing works out that you can check in various cases that this is in fact positive. And so this is the part which is which we're still finishing out, which hasn't yet been.
So you can call it the free part and the interactive part?
Yeah. When you compute these contributions to the anomalies, you can basically just add up all of the contributions. So there are all the contributions from the free fields, which end up giving these free field values. And then there's an extra piece, which basically, it's like, because you have to cancel this term by something that you square, you end up with another term that involves C2 of R squared, and that contributes to this alpha, just from completing the square. And so this alpha gets an extra contribution, which contributes positively to A. And so in the end, it works out that this A is positive, but initially we were bothered by the fact that these mixed anomalies, this prescription was kind of assuming that these mixed anomalies vanish. And we know that there are perfectly fine theories where they don't vanish, like the small SO32 instanton theory. But then it actually followed from our classification that it had to vanish because there wasn't a corresponding operator to play the role of the thing on the right-hand side of the anomaly equation.
When you wrote down the data for the small 8 instanton, it was the same data for the small SO32 instanton. The part that you wrote about the H part, dimension, and the dimension, the tensor part, at the same number. So where do they have different contributions from this?
Oh, they're totally different. The SO32, the small instanton, and the small 8 instanton are very different.
So different data.
Yeah, they have completely different data. Turns out. Yeah, I mean, it's true that you can relate one to the other by contractifying in the little string version, but yeah, their data is completely different.
Do you have it for cases?
For the small SO? Yeah, so the small SO32 instanton theory, if they're so this is the theory that was written out by Witten. There's an ST2 engaged theory with a half hyper multiplet in the 2n, 32. There's an SO32 global symmetry. And then there's an anti-symmetric 2-index tensor. So
I think we may start when we
okay.
wrap up.
Okay. Yeah, maybe we can switch to 5 minutes. Yeah. So anyway, you can compute it from this table for that theory, and it ends up being very different. Yeah. Sorry.